My name is Trong-Thuc Hoang, and our lab we're doing with RISC-V and security for like nearly 5 years now, and we are aiming for the complete system with the cryptographic accelerator, and we're choosing the sorry, I need to full screen. And we're choosing the TOS 1.3, the latest one, for like a guideline for us to develop the new crypto core for the RISC-V system. So first is about the introduction. So you know that the TOS is the successor of the SSL, is maybe one of the most common use among the internet. So the latest proposal is the version 1.3 in 2018. So it equipped with current like update for new cryptography algorithms. And although the workflow of 1.3 is not fixed yet, but many crypto functions like the old crypto algorithms are left as optional, and there are also many new crypto algorithms included in. So we use the TOS 1.3 as a guideline for us to develop all of the cryptography accelerator using the RISC-V-based system. Here is the list of support algorithm in the TOS 1.3. Some are mandatory and some recommended, and some are just option, like for back support. So the key algorithm here is the ED, EC. Could you see the ED DSA and the ED, also the one of elliptic curve, the HMA, the ASGCM, and the new Chachapoli is the one that they included very recently, and the good old SAR2 and SAR3 and RSA. So we aim to include all of this into the new developed RISC-V by SoC. First, about the system, it's very, I think, most standard system with the simple rocket or boom cores. We can choose which type of processor to be used, like rocket or boom, or we can choose the ISA or the number of cores. All of the like the tiling, the PCIe and the memory and the peripheral, all of that are configurable. They can be included or excluded. You can choose to use with the Linux or not, depend on what the requirement you want. So the memory bus have two options of using the on-chip RAM or the off-chip DDR or both. And the peripheral bus divided into two groups of utility and the crypto core. The utility is just very basic function like boot ROM for the SBL, the SD card for holding the FSBL and the Linux image, and the UART for communication. And in the crypto core group, we have all of the above mentioned core like SAR2, like SAR3, like Chachapoli, like RSA, like ED, ECDSA, HMA, etc. Now we go for each individual of the crypto core. First is the TING. This is the core based on the frequency collapse and the ring oscillator, and we already have published one paper about this. You can see the link in here. This core, the blue one, the core have passed on the NIST and the IAS test. The second one is the RSA 1024-bit. The goal is just to minimize the area by using the less big, like less full 1024-bit register as much as possible. A small task like get number of bit, add sub or comparator are doing by primitive, and they executed only 32 bit at a time. So the goal is just reduce the size while also provide the hardware accelerator solution. Next one is the AES GCM. GCM stands for Garros Counter Mode. This one is mandatory in the TOS 1.3. This core have support encryption and decryption, can have two modes of 128 bit or 256 bit. Next is the SAR3 or the CAT card. This one supports 512 bit, and the core are actually based on the open source project. Next one is the HMUS. HMUS is among the MARC family, the method authentication code, and hash-based, we call it HMUS, and it's based on SAR2. This core also have two modes. You can use it at only SAR2 like a normal hash function, or use it at the HMUS SAR. Support 3 bit of 256, 384, and 512. This one is the new added in the TOS 1.3. It's called the Cha-Cha 20. It belongs to the stream cipher text and was standardized very recently. This can work along or team up with the poly to perform the AEAD, the authenticated encryption with the addition data. Next, of course, is the poly. This is among the MARC family, and also very recently standardized. This can work along and or team up with the Cha-Cha to perform the AEAD. So we have the Cha-Cha, we have the poly standalone, and also we have the AEAD using the above mentioned Cha-Cha and poly cores. So we also have published one paper about this implementation. The final core is the ED, the elliptic curve DSA, and the ED and the EC together. So this core support up to 4 curves of the elliptic curve, the 3 curve of the ED, and the 1 curve of the the 3 curve of the EC and 1 curve of the ED, and support 3 type of bit, and also support 3 type of function: gen, key, sign, verify. So the goal is provide the multi-mode, multi-purpose, and small and compact and hardware accelerator solution for the SoC. We have the one paper for the implementation just this February of this year. So next is the implement on both FPGA and the SoC. First, about the FPGA, we're choosing the Vertex 7 on the VC707 FPGA board. So the build board in here with all the 9 crypto core in the lookup table, register, program, RISC-V, and the maximum frequency are on the list in here. And in the full system of the SoC, we also have the pie chart for the lookup table utilization, register utilization, all the crypto core are included, and 1 processor of the Rocket chip, 32-bit IMAC. The rest is just mean on the buses and on of the GPIO and boot RAM, etc. So you can see that the Rocket still hold, I think, the big register, and the RSA with all of the sub and get number of bit, and the comparator is hold a lot of combinational logic, and the rest is very small, like AAD, SAT3, poly, Cha-Cha hold very small percent of the lookup table and register. We also synthesize in the ROM 180 nanometer, and this show the synthesis result of all the 9 core at the synthesis state and also at the PNR state. The number of cells, the area. Some core has the RAM, like HMUS using the SRAM. Have the power, the maximum frequency. At the PNR, we have the density of the core could go up to nearly 80%. The number of MOSFET all are listed in here, and similar with the previous FPGA implementation, we also have the pie chart for the ROM synthesis. Also, all the crypto core are included, with one single core of rocket chip, 32-bit IMOC, in the area and in the power. Yeah. So the rocket also still hold the majority of the area. And we also fabricate one chip in just February of this year and expected to be delivered in this month. Actually, I think it will be delivered in maybe the end of this month or the next month. So you can see the floor plan of the chip in here. What with one core of rocket, 32-bit, on with the 9 core 1, 2, 3, 4, 5, 6, 7, 8, and the TNG inside. So 9 core, and the rest of the buses, peripheral, central, and here. Because we didn't have the chip yet, so I just showed the image of the layout, and all the key feature of the chip is summarized in here. So one core rocket, the ISA 32-bit with 16 kilobyte of for I cache and D cache, on the 9 crypto core included. The number of cells, the area. This chip is 5x5, so the area of the core fit very nicely in the die of 5x5 millimeter square. The overall density about 71%, about 8 million of MOSFETs. And similarly, also plot the pie chart for the area. And all of the components are break down in here. You can see it in the percentage. And the rocket type also still hold the majority. And again, for the power. To test all of the crypto core, we developed 2 kinds of tests. First one is at the M mode during the boot time in the FSBL. Second one is after boot. We also developed some driver and assemble text for testing the hardware after boot into the Linux. Yeah. So for conclusion, this is the RISC-V-based SoC completed development for aiming for TOS 1.3, and all the 9 crypto core included, aiming for the flexibility and compact. Like you can see that many core have multi-mode and multifunction. And the proposed design will verify and test on both FPGA and VSI implementation. And also one real chip already made, and we are waiting for the chip to be delivered to measure it. Yeah, thank you.
So you added the cryptographic extensions to your RISC-V core. So maybe you already told about this. Sorry if I couldn't catch, but so how to implement such a cryptographic extension functions? Is it RTL by scratch hand or something like for other methodologies?
How to develop, like, sorry, could you repeat the question again?
Yeah, how to develop or add cryptographic function into, so crypto core is, yeah. So how to design this? Just a simple question. Sorry. Yeah.
So it's based on the standard. Each core here, I also include a link for the standard. For example, this link is just linked to the standard, like the guideline on the standard on the algorithm. That's it, and we base on that, and we understand that. We do the simulation first, and then we do the design. And after that, the testing on the Verilog, and after that the testing on the software. That's it. Yes. So they are just the standard, the link of the standardization.
Okay, so yeah, it's yes, basically such a basic cryptographic functions. It's a hardware of cryptographic accelerator or so, I think. And also instruction decoder is added about the cryptographic extensions, I guess. So is it also in some standard method to add the instruction?
For the instruction to use the crypto core, because we add it in the crypto robust, so we only use it like read and write register. So there is no custom instruction in here. It's just a normal read and write transaction into register inside the crypto core, and based on that we do the driver. So it just read and write the register inside the core.
Oh, really? It's mainly by the driver.
Because it's on the peripheral, so it just register map the address.
Okay. So it's not implemented as some specific instruction of cryptographic extensions. Okay. And another question from me. So you estimate or you analyze the power dissipation on the SHA or such a RISC cryptographic running. So this is about which softwares? Is it a bootloader or such a software, or some special cryptographic application software?
For the power, on FPGA, when we do the compilation, we have the resources utilization, and that just report the static power of the board.
Really?
For the chip, because we didn't receive the chip yet, so this result is just the synthesis result of the chip that we fabricated, and the synthesis result the static power.
Yes, okay. Then just still no question from audience. So so you have comparison between the fabrication processes. So yeah, this just now slide shows a low 180 chip process, and another one. So this process is some. So do you have some reason why you use this low 180 chip process, or is just a standard one, or used to make a chip?
Yes. Traditionally, in our lab, we have the ROM 180. We have the SOTB, which belong to the Renaissance 65 nanometer, and we also can do the TSMC 65 nanometer. So the choice of 180, the choice of ROM is just because it's cheaper and it's supported by the VDEC. Yes. In the future, we would like to try the tablets also.
Okay. So, still no question from audience. So, thank you so much. A little early time, but yeah. So it's very meaningful and interesting presentation. So
yeah.
Yeah, I think it's it's still early time, but no question from audience and yeah, sorry, but yes.
If you have any, you could ask me on the email.